Welcome to the 11th lecture of graph theory. In the last class, we were discussing Mengers theorem in this generalized setup. So, we considered a graph and two subsets A and B of the vertex set of G. So, Mengers theorem states the minimum number of vertices separating A from B in G is equal to the maximum number of disjoint AB paths in G. We had discussed what is meant by a collection of vertices to separate A from B, which means that when you remove those collection of vertices, then there won't be any more paths from A to B, from the remaining vertices of A in G, A to the remaining vertices of G. It is possible that we may remove vertices from A or B or both. Maximum number of disjoint AB paths. AB path means a path which starts in A and ends in B, but this path will take exactly one vertex from B, A, and exactly one vertex from B. That means the starting vertex of the path will be in A, no other vertex of the path will be in A, and similarly the ending vertex of the path will be in B, no other vertex of this path will be in B. Such paths are AB path. We are interested in disjoint AB paths, so they should not have any common vertices in these paths. How many is the question. This maximum number between a given pair AB of subsets of phi of G, this is equal to the minimum number of vertices separating A from G. So, today we are going to do the proof of this statement. So, we are going to prove this by induction on the number of edges in the graph. So, you can consider an end node graph G. So, G equal to V comma E. So, the n node graphs, in the n node graph, so suppose there are no edges, that means 0 edges, our induction is on the number of edges. So, there are no edges, then the minimum number of vertices to separate, and also your A and B are given, both are subsets of V, is the before getting into that, we should notice that if there are suppose some t number of disjoint AB paths. Now, to separate A from B, we need to remove at least one vertex from each of this path. Otherwise, the path from which no vertex is removed will remain in the graph. So, an AB path will remain. So, A will not get separated from B by removing whatever we did, right. So, therefore, at least t vertices we will have to remove if we want to separate A from B. So, if you write k comma A comma B comma G to denote the number of vertices required to separate A from B in G, then this has to be definitely greater than equal to t, the number of disjoint AB paths, maximum number of disjoint AB paths. The question is, can it be strictly less? That means, can we show that if k is the number of vertices that is to be removed in order to separate A from B, then do we always have t disjoint AB paths in the graph? Now, if I am given A and B in a graph without any edges, then it is very clear that to separate A from B, we just have to remove the vertices which are common to A and B. That means, for instance, A can be like this, B can be like this. Then if you want to separate it, this vertex and this vertex is to be removed, and these are the ones to be removed, these are the only ones to be removed. So, in this case, the minimum number of vertices that is to be removed from the graph so that A gets separated from B is equal to A intersection B. So, of course, corresponding to each vertex in A intersection B, we have one AB path, because that is a trivial AB path having just one node. It starts in A and ends in B, because both this vertex belongs to both A and B. So, therefore, we do get so many AB paths also. So, in this case, when there are no edges, the statement is trivial. So, we can assume that there are some edges. So, we started off the induction now. Now, there are some edges. We pick up some edge xy. This is xy in the graph. This is G. And our plan is to contract this vertex to get a new vertex Vy. What is the advantage? We have, by doing this thing, we have reduced the number of edges, and for all graphs with smaller number of edges, we are assuming the theorem. So, the first question that comes to your mind, okay, so I am going to use induction on the smaller graph with the smaller number of edges for on the same sets A and B. But the first question that comes to mind is, will this A and B remain same? Of course, the A and B need not remain same, because we have destroyed two vertices x and y and created new vertex v x y. X and y was converted to a contracted vertex v x y. So, if A and B contained x or y or both, then the set is going to change, A and B are going to change. So, what we will do is, suppose A, say for a set A, it did not contain x or y, then it is as such, we will not have any change for A. But if it contained x, then we will add v x y to it. Similarly, if it contained y, we will add v x y to it. If it contained both, then also we will add v x y to it. Similarly, for B, suppose B did not have x or y, then B is as such, it will not be affected by this contraction operation. But if x or y was present in B, then we will put v x y in it. Also, if both x and y were present, then also we will put v x y in it. So, what we should notice is, it is possible that v x y may be added to both A and B. It is not just that if I add v x y to A, then I cannot add v x y to B. So, it is possible that we may add v x y to both of them. Now, the idea is to ask this question first. So, now is it possible that, see, we have this graph G, A, the two sets A and B, and we know that the minimum number of edge vertices to be removed from the graph so that A gets separated from B is exactly k. That is the number we are this the letter we are using to denote the number of vertices required to separate A from B, right, k of A comma B comma G. Sorry. Okay, so this is the letter. Now, we also assume that there are no k disjoint AB paths in G. If there are already k disjoint AB paths, we do not have to prove anything. So, we assume that the maximum number of disjoint AB paths in G is strictly less than k. Now, the first question is, suppose I do the contraction operation and I get a smaller graph, say G dash. Is it possible that in G dash suddenly we have k disjoint AB paths, A and B as defined just above? It may get modified, but as above, as I described above. Is it possible that we end up with k disjoint AB paths in G dash? So, suppose it happens. Suppose it happens, then why can't we use the same AB paths in G also? That is the question. So, if these AB paths were without that new vertex Vxy, the contracted vertex Vxy, definitely those paths will be available in G also. We could definitely use them, and therefore, that will be contradicting the assumption that there are no we do not have k AB paths in G. So, if at all G dash has k AB paths, the newly created vertex Vxy by contracting x and y should participate in these paths, but it cannot participate in every path. It can only participate in one path, right, because these are disjoint AB paths. Should be at least one of these paths should contain Vxy. Then why don't I try to convert it to an AB corresponding AB path in G. So, for instance, all the other k minus 1 AB paths can be used as such, and this Vxy we can replace by the original xy. What will happen? So, this path, is it possible? It is possible. Suppose the path is there, this Vxy, it is possible that x and y, when I separate it, it may look like this. Then of course, x takes path in the path and it is okay, or it may be just that these two edges, both these two edges which are participating might have come from y. Then also we can put y and we get the corresponding path, or it may be possible that this edge came from x, one of the edge came from x and the other edge came from y. So, by putting back x y, we do have the AB path again, just that we are elongating the path by one more edge, because we will if this was the path before, we may make it like this being x and y. This is possible, right. This is the disjoint AB paths. So, what we can understand is, in G dash, that means after contracting the edge xy, the resulting graph, if we have k AB paths, then the same KB paths, or maybe with some little modification, will be available in G also, the original graph also, that instead of Vxy may have to use x or y or xy, right. So, therefore, it is not possible to have G dash to have k AB paths, right. G dash also will not have k AB paths. So, we can say that k dash does not have. So, G dash also does not have k AB paths, otherwise G also will have, which will be a contradiction. Now, if G dash does not have k AB paths, so suppose it has k minus 1 AB paths, if it has k minus 1 AB paths. So, this k minus 1 AB paths means that there are, by induction hypothesis, because we know that for all smaller graphs the induction was true, the statement was true. That means k minus 1 AB paths means the number of vertices to separate A from B there has to be k minus 1, right. So, it has to be k minus 1, right. So, this is k minus 1, is not it. So, you can separate A from B using k minus 1, some k minus 1 set y. So, let us call it this set as x. Some set x will separate A from B and it will contain only k minus 1 vertices, right. So, you may ask why it is not k there, because if it is k there, induction has to be true there. So, so it would mean that there will be k AB paths. So, you can only have k minus 1 AB paths. You know, now you should ask, okay, if there is a k minus 1 sized separator of A and B in G dash, where will be Vxy, our Vxy? Is it possible that Vxy is totally inside A, Of course not, because if Vxy is totally here, I could have replaced Vxy with the original edge xy here, and this x will again separate a from b, right. So, it is very clear, because it does not change anything, because there will not be, when you remove it, you cannot introduce any new x ab paths. Similarly, x and y, both of them cannot, sorry, Vxy cannot be here also, right, because I would have replaced xy Vxy with this edge xy, and then now when I remove x, there will not be any AB paths left. So, there will not be any AB paths. So, x would be a separator of A and B. It would contradict the assumption that there is a there is a the separation, the number of vertices, minimum number of vertices to separate A from B is k. So, you could not have separated A from B using just k minus 1 vertices. So, what do we infer? We mean that the contracted vertex Vxy cannot be in this side, sorry, or in this side, not A or B. I mean whatever is separated, now x is separated by this thing. So, it is not possible to have Vxy outside x. So, you should have xy, sorry, it is not A. So, whatever. So, it is, because if Vxy is outside x, then we could have put it back, that edge we could have put it back without affecting this thing, because whatever we remove here is the same, and then this will not be capable of creating an AB path here. So, Vxy has to be in this separator. So, x and y has to be in separator. So, what we do is, so this is not Vxy. So, Vxy could be replaced by original xy. What will happen? So, the x will get converted to a separator x dash now, which is essentially x minus Vxy union x comma y, right. So, instead of Vxy, I am putting x and y in this thing. So, we will call it x dash. So, this x dash is a separator for A and B in G also, is not it? X dash is a separator for A and B in G also. So, because if you remove x dash, then it is like removing x in the smaller thing, right. The only thing is there are one more vertex now. So, it is a k separator, not k minus 1 separator, right. So, now let us consider this x dash separator here. This is the x dash separator. Now, we have A somewhere here, B somewhere here. So, this A is separated from B by x dash in G itself. Now, we consider this A x dash separator in G. What we can do is, we can remove this xy edge from the graph, right. X and y both are in x dash. So, therefore, the induction hypothesis holds here, right, in a smaller graph. But then see, what about, suppose there is a separator y which separates A from x dash. So, what can we tell about the cardinality of y? Can it be greater than k? No, it cannot be greater than k, because x dash itself is a Ax dash, separator of A and x dash. So, x dash is only cardinality k. So, therefore, it cannot be greater than k, it should be at most k, but can it be less than k? But if it is less than k, then what will happen is, so in every A x dash path is separated a cut or is passing through this y, right. That is why y can separate A from x dash. Now, also we know that every A to B path is passing through x dash. So, now any A to B path in G has to pass through x dash. That path is also passing through y, because y is an Ax dash separator. So, when you remove y from the graph, a will get cut from x dash. So, it means that a will get cut from b also, separated from b also, because all the paths which starts in a and go to b should pass through x. All the path that starts from a and reaches x dash has to pass through y. So, all the paths that starts from a and reaches b has to pass through y. So, when y is gone, a is separated from b. So, y has to be of the cardinality k. So, otherwise we will have a smaller cardinality separator of a and b in G, which is not possible. K is the minimum number of vertices required to separate it by assumption. So, therefore, we can definitely assume that the cardinality of any Ax dash separator is equal to y, it is equal to k. And now, what about B? Suppose if I consider a separator y dash of B x dash, the same argument is true here. Its cardinality has to be k. Why? Because it cannot be more than k, because x dash itself is a separator and x dash is of cardinality only k. And now, every B A path has to pass through x dash, and then every B x dash path has to pass through y. That means, every B A path has to pass through y. So, essentially y dash. So, which means that the y dash has to be of cardinality k. Now, because we can apply induction hypothesis here for G dash, because we have removed this one edge, that is why x y edge we can remove and argue, then that means there are so many Ax dash paths also, right, the k Ax dash paths also coming from A to x dash and coming from B to x dash, like k dash B x dash disjoint paths are available. Similarly, k A x dash disjoint paths are available, that is by induction. But you may ask me, suppose if I put back this edge, is it possible that number of vertices required to separate A from x dash will change? So, it is not possible to change, because this y edge is added inside x dash, that is not going to change anything, because if it is separated by y, now putting an edge between x and y, how does it change the situation? Because if x was in A, then if x was not gone, then it is not separated. So, we can assume that x and y, if it is still there, then it is not part of A, right. So, otherwise putting a connection between x and y is not going to provide a path from x to A, x dash to A. Therefore, whether the edge x dash x y is there or not, y will remain as an A x dash separator and y dash will remain as a B y p x dash separator. So, it means that we can say that even with this new edge x y, that means original graph G, we have k disjoint A x dash paths in G, and similarly k disjoint B x dash paths in G. So, we will get a picture like this. So, this is x dash, this is A. So, we will get some paths like this, k of them. So, because there are k, similarly here this is B. So, here we will get k disjoint paths. You remember the x cardinality of x dash is equal to k. Therefore, the n vertices are just sufficient to fill all the vertices, it takes up the n vertices of this A, B, A x dash paths take up all the vertices of x dash. Something starts from here, ends in one vertex, another vertex, another vertex, another vertex, there is nothing left here. Similarly, this B x dash paths also come and take up these vertices. So, there should be one for each one vertex, there should be an A x dash paths, a B x dash path, like that. So, they will merge like this, right. For every vertex there will be one coming from the A side, one coming from B side. So, I can start from A, reach this vertex and go to B, right. So, these are disjoint anyway, is not it. So, you should see, so it is not that this portion will take something from this portion. In that case, we would have got a B path which does not go through x dash. So, they cannot take anything from that, because here there is the first vertex in A, there is the first vertex in x dash. Similarly, there is one here. If something goes and takes here, then you could have short circuited and got a path between A and B which does not go through x dash. That means x dash does not separate A and B. So, we can paste the paths together and we get k disjoint A B paths in G, right, as we need it. That is what we wanted to prove. We wanted, initially we started off proving that if x dash is a separator of A and B of cardinality k, then we should have k disjoint A B paths in G. So, we ended up proving that. So, we in the last class we had seen the applications, how this generalized version of Mengers theorem can give us back the original Mengers theorem, that whenever two vertices are considered, the number of vertices other than A and B required to be removed from the graph, so that A is separated from B. This number is the same as the number of vertex disjoint internally vertex disjoint A B paths in G. Such things we had already seen in the last class. Now, okay, the only thing probably which remains regarding Mengers theorem is to look at its edge version. So, to look at the edge version of the Mengers theorem, one easy thing to do. So, rather than proving it separately, is to consider it to derive it from the vertex version of the Mengers theorem in as follows. So, let us just talk about a construction called line graph construction. Line graph construction. What is a line graph construction? So, for instance, you can consider this graph. So, small graph here. So, right, here is say E1, E2, E3, E4, E5, E6, E7. So, these 7 edges are there here. Now, I can construct a graph on 7 vertices. So, this is E1, this is E2, this is E3, this is E4, this is E5, E6 and E7. Now, E1, E2 is a connection, E1, E3 there is a connection, E2, E3 there is a connection, and E1, E6 there is a connection. So, what I am going to do is here, whenever this E1 two edges E1 and E2 are adjacent, then I am putting a connection between them. So, here this is E1, this edge E1 is connected to this edge E2. So, E1, therefore, I am this is the edge E1, this is the edge E2, then I am putting an edge between them, right. And similarly, you consider E3. So, E3 and E1 is adjacent because they are adjacent incident on the same vertex. So, I put a edge between them. Similarly, if I consider this is E8, sorry, E6 and E1 are adjacent. What about E2 and E5? E2 and E5 are adjacent because they are sharing an edge here. So, E2 and E5 are adjacent, you put an edge between them. E2 and E4 are not adjacent because E2 is here, its both endpoints are different from the both endpoints of E4. So, there is no vertex, no connection between them, right. So, this is E2 and E4 are not adjacent. Now, E4 and E5 are also not adjacent, right? This edge is not there because this are not sharing any endpoints, but on the other hand E5 and E7 are adjacent this way. So, if I construct a graph like this from this graph, then it is called a line graph. So, here in the line graph, the vertex set is the set of edges of this, and then two vertices here will be connected. If the two vertices here are in fact two edges of this graph, and whenever these two edges share an endpoint in this graph, we will connect them together with an edge. This is the line graph, right, construction. So, what is good about line graph construction? So, see, to understand the line graph, we can construct some simple examples. For instance, this is the Cn, the cycle. What will be the line graph of this Cn? Of course, it will be Cn itself. If we put some this thing, you can see that the same cycle will come, right? Because the edge will, this edge will become a vertex. That's the only thing. But then the two vertices will be adjacent to this. So, it's same cycle will come here. So, for instance, if you consider a complete graph Kn, and we call it the line graph of Kn, the line graph of G. So, given a G, we will write line graph of G, right. So, in the line graph of Kn, the number of vertices will be n choose 2, because there are n choose 2 edges in Kn, and then whenever two edges are adjacent, then we will have to connect them together, right. So, for instance, we can consider a k regular graph G, k regular graph G, k regular graph G. So, how many edges are there in the graph G? There are n into k by 2 edges in G. In G. So, n k by 2 vertices in the line graph of G, L of G, right. Now, you may ask, so what is L of G a regular graph? Yes, it is a regular graph. What should be the degree of each vertex in L of G? So, because if you look at G, this is an edge in G, this is going to be a vertex in the other line graph of G. Now, the neighbors of it is going to be this edges and this edges, right, this edges. So, how many of them are there? Because it is a k regular graph, there are k minus 1 here, there are k minus 1 here, total degree will be 2k minus 2, right. So, this is this is a typical situation in line graph. So, for instance, if you look at a vertex V and the edges incident on E of V, let us say, vertex incident on the vertex V in G, what will happen to this in the line graph? This will become, because these are all these vertices, if you see, they will all be adjacent to each other in the line graph, right. So, that will become a clique in L of G, right. They will form a clique in L of G. So, this I told all these things to just make you familiar with the concept of line graph. Why do we have, so when do we call a graph is a line graph? So, we call a graph a line graph when we can find some other graph H, so that G is the line graph of H. So, in other words, if we know that G can be represented as the line graph of some other graph, then we can call this graph a line graph, right. So, usually we will say, okay, this is a graph and here is the line graph of it. Then sometimes we will simply say this graph is a line graph, because we just want to say that this graph, there is some other graph such that this graph can be represented as the line graph of it. So, that is the notion of line graph. Now, how does the line graph helps us to do the edge version of the Mengers theorem? So, let us look at the edge version of the Mengers theorem. So, this is the minimum number of edges separating A from B. A and B are two vertices in G. Suppose the minimum number of edges separating A from B in G is equal to the maximum number of edge disjoint AB paths in G. That means you are given two vertices. So, consider the minimum number of edges that is to be removed from the graph, so that A and B are in two different components that results from this removal of edges, right. Now, you also ask how many maximum number of how many edge disjoint paths between A and B can be found out in G. So, both these numbers are same. So, how do we do this thing? So, to do this thing, so we should use the line graph concept. We would consider the line graph of G, and then all the edges of G will become vertices there. Now, for we are given two vertices A and B, right. So, the incident vertices on A would have become a collection of incident edges on A would have become a collection of vertices in the line graph. This collection of vertices are collected, and let us call say that it is E of A, and similarly collection of edges which are incident on B would become a collection of vertices in the line graph. So, we will collect that vertices. So, now between E of A and E of B, between E of A and E of B, we consider the separator A equal to E of A, B equal to E of B. The number of the vertices required to separate A from B is essentially equal to the number of edges that need to be removed from the original graph, so that A gets separated from B in the original graph. Similarly, the number of disjoint AB paths in this line graph will be what the vertex version here, right. So, in the it will be equal to the number of edge disjoint AB paths in the original graph, AB paths in the original graph. So, therefore, just apply the Mengers theorem here, you will get the edge version of the line graph there. So, we will just look at the statement. The statement is just this: the minimum number of edges separating A from B G is equal to the maximum number of edge disjoint AB paths in G. Maximum number of edge disjoint AB paths in G. Now, a graph is k edge connected if and only if it contains k edge disjoint paths between any two vertices. Graph is k edge connected if and only if it contains k edge disjoint paths between any two vertices. So, what do I mean by k edge connected? We already discussed it. It means to disconnect the graph we need to remove at least k edges, right. So, it happens only if there is, for given any two vertices, there should be k edge disjoint paths, that's the same as the graph being edge connected, right. This is an immediate consequence of what we just saw before. So, we therefore, anyway, you just have to think about it to understand what it is. And now we close with this Mengers theorem. We will look at a slightly different notion of connectivity called linkedness. What do we mean by linkedness? So, here let G be a graph, then let X subset of V of G. We say that X is linked in G. If whenever we pick distinct vertices S1, S2, Sk and T1, T2, Tk in X, we can find disjoint paths P1 to Pk in G such that each Pi links Si to Ti and has no inner vertex in X. So, in other words, if V of G is greater than or equal to, and also what is linkedness, if V of G is greater than or equal to 2k, suppose there are 2k vertices in the graph, every set of at most 2k vertices is linked in G. Every set of at most 2k vertices is linked in G, then G is k linked, then G is k linked. Equivalently, a graph G is k linked if disjoint paths P1 to Pk, where Pi is from Si to Ti exists for every choice of exactly 2k vertices. So, these are all equivalent notions. So, let us try to explain this. So, the final thing is much easier to understand. So, here we are saying you give me whatever way you like, you number S1, S2 up to Sk, some k vertices, say, and this can be called source vertices, some other disjoint different vertices T1, T2, Tk as sink vertices. Now, somehow this S1 and T1 is one pair, right, source sink pair, this is another source sink pair, this is another source sink pair. Now, we should be able to find a path P1 between S1 and T1 and a path P2 between S2 and T2 and a path Pk between Sk and Tk, right. So, this path should be disjoint, they should not share any vertices, even the endpoint should not be shared. And see, the key thing is, of course, these paths, some paths do exist between this k set and this k set by just connecting it. If the graph is k connected, we know that between these two sets we do have k disjoint paths, but it is not enough here. Here we are also, the enemy is also allowed to number the S1, S2 up to Sk, the T1, T2. So, we may find these paths, then they may say that I want one. So, this is T1 now and this is T2. So, you may interchange the role of T1 and T2 and then ask for new paths, new set of paths. Or in other words, if you fix this S1, S2 up to Sk here in one order, it is possible for this T's to appear in any of the permutation, in any of the order, this T1, T2, Tk, or Tk may take the role of T1 or anything may take the role of T1, any permutation is possible here. We should be able to match them in such a way that this is matched to this is matched to this, and right, that means we should find. So, there should be so many paths, so many paths. So, the question is how good should be the connectivity for this to happen. So, of course, the k connectivity is not enough, we can simply take some examples. For instance, see this cycle, we know that Cn is 2 connected, right, any 2 vertices, if you take, you can find 2 paths. So, or any so 2 paths are available, or if you get 2 vertices, I can show one. So, this 2 sets, this is A, this is B, I can indeed find one path here, one path here, right. But what if I say this is x1, sorry, this is S1 and this is S2 and this is, so I name this in a wrong way, that means I will say, I will call this T2 and this as T1. Then from S1 to T1, if I want to find a path, I either have to come like this, right, come like this, in which case I will already take up T2. So, that is not allowed, because T2 S2 path should contain T2 and then that intersection is not allowed. Or if I try to come this way, then S2 will be already inside this, that is also not allowed. So, in this case, if I take S1 here and S2 here and T2 here and T1 here, then I am stuck. I can have only, I cannot have paths from S1 to T1 and S2 to T2 which do not intersect with each other, right. So, that is a problem. So, we we can say that if I give S1 and T1, then I can find a path, but if you give S1 comma S2 T1 comma T2, then I cannot guarantee, it depends on, right, how S1 S2 S3 are arranged. So, the k linkness demands that in a graph, if you are given S1 S2 Sk in whichever vertices it are, whichever naming it is, and T1 T2 Tk and different set of vertices from S1 S2 Sk, and whichever is the naming, right, irrespective of that, we should be able to find from S1 to T1 and S2 to T2 S2 3T Sk to Tk the disjoint paths pk, p1, p2, p3, pk, right. This path should be available, otherwise it is not k linked. So, in the cycle, though it is 2 connected, it is not 2 linked. So, you can try even this, for instance, you take this wheel structure which is 3 connected in fact. So, right, if you take any 2 vertices, you can get 3 paths here. For instance, if you take a vertex here and a vertex here, so this is a wheel of case. So, right. So, you can always go through the center, and also you can go through this and this, there are 3 paths. So, but it is not even 2 linked. So, the question is, of course, is it 3 linked? Of course, it is not 3 linked, it is not even 2 linked, because you can take this S1 and S2, right, S1 S2, and then we can, as usual, we can take our T1 and T2 here. What will you do? To here. So, of course, we can try to make use of the central vertex, but it does not help, because S1 to T1, if you use this, right, if you use this, of course, the center is not available for the other pair anymore, right. Now, the other pair T1, T2, if I am trying to go like this, S1 is blocking it. If I am going to like this, T1 is blocking it. So, both ways I cannot go, neither is this possible, nor is this possible, and nor is this possible, because this vertex is already taken, by the other path. So, here you can see that even with the 3 connectivity, it is not happening, right, in general. So, I can say that right. So, but on the other hand, there are in some cases the k linkness may be very easy in some cases. For instance, in a complete graph Kn, you can say that see any k set, right, any n by 2 set, if you take another n by 2 set is available. So, we do get between any of them a path, right. So, you just have to tell which Si, which Ti, we can always give the paths required. So, 2 length paths, like 2 vertex paths, right, and edges can be given. So, they are n by 2 linked, but on see, on the other hand, the relevant question is, suppose I want the graph to be suppose the graph is to be k linked, right, k linked, then how high should be the connectivity to ensure this? Should be the connectivity, or how should I keep the connectivity to ensure this, to guarantee this? This is the question. How high should I keep the connectivity to? Is it so? We have seen that the connectivity, if the connectivity is just k, it may not happen, as in the case of the as in the case of the cycle Cn, or in the case of wheel, it was 1 more, but still it was not happening. So, for instance, up to where? For instance, you can see this example, this simple example. Here we have a 2k minus 1 connected graph. So, you take a clique of 2k minus 1 here, 2k minus 1 clique, this is a clique, and the 2k minus 1 clique here, right. So, 2k minus 1, and then the corresponding vertices you just connect like this, matching. So, just match them here, right. Now, what is the connectivity of this thing? For instance, if you want to inspect the connection between these 2 vertices, right. So, we have how many paths between them? So, each of the intermediate vertices will give one path like this, and one direct path is there, right. So, total we have 2k minus 2 plus 1 path is there, because it is always possible to go to this side and come also, 2k minus 1 paths are there, right. So, we have to, so this 2 vertices 2k minus 2, see other than see how many vertices are to be removed from the graph so that these 2 vertices get disconnected. That way also you can ask, right? So if you leave even one vertex left here, there will be a path. So you will have to remove all the 2k minus 2 vertices here. How many vertices are removed? So this is 2k minus 2 vertices, sorry, 2k minus 3 vertices here, and you have to remove at least one more from here, right? This is 2k minus 2 connected. This graph cannot be k-linked. Why? Because see the simple argument here, because if you look at, say, vertices, say the k vertices here, 2 3 1 2 3 4 k vertices here, and then you just say that this is my S1, this is my S2, and this is my SK. Now here I would rather say this is the second vertex here is my T1, and the third vertex is T2, and this is Tk minus 1, and this is Tk. Let me just rotate it, the destinations. The direct connection is not there between S1 and T1. This is S1 is connected to Tk, rather T2 is 2 is connected to T1, and 3 is connected, k is connected to Tk minus, and on and so on. Now we have only k minus 1 vertices left here, right? So you can see that if I want to travel from here to here for any pair here to here, you cannot use this direct edge because it will eat up one of the destination vertices. So that's not allowed. So you have to, the only other way to go to this group and then go to this side and then jump into this, right? So every time for every pair I have to use one from here, right? But there are only k minus 1 vertices here. So finally what will happen is I will not be able to, for one pair I will not be able to get these resources available. So k minus 1 will finish off for k minus 1. So one pair will not be able to connect between each other. That's it. So that is the that is the reason why this is not k-linked. So we have showed. So in other words, so even with some connectivity like 2k minus 2, we are unable to k-link it. But it is shown that we won't show it in this class, that if the connectivity is 2k with the assumption that the average degree is also a little bit, there are the number of edges is a little more than just implied by the connectivity, then it is indeed k-linked. That is proven by Thomas and Wallen. That proof we will not do in this class, but we will do some we will do a little lighter version of that. Of course, we will just show that if you keep the connectivity sufficiently large, then it is possible to k-link the graphs to ensure that, to guarantee that the graph is k-linked. But otherwise, so in fact the statement can be improved, as I just mentioned, to say that if the graph is too connected and then the average degree is a little higher, 8k or something, then it can be shown that it is k-linked. So that will be done in the next class. So next class we will do a proof of this statement that if the connectivity is sufficiently large, then the graph has to be necessarily k-linked. So to summarize today's class, what we did is we did a proof of Mengers theorem for the generalized version, and then showed that through the line graph construction the edge version of the Mengers theorem can be derived from the vertex version, and then we discussed about this slightly stronger version of connectivity called K-linkedness, and that will be discussed. The proof of this particular statement which I just mentioned will be discussed in the next class. Thank you.